All right, this is a video just talking about another example of integration by partial fractions. I would always urge you to kind of follow a step-by-step process of ruling out integration techniques. The first thing, of course, to look at is, can I do this by some old technique I learned? Just, is it just undoing power rule or undoing a trig function or something easy like that? This is obviously not that. It's a quotient. It looks pretty complicated. The next thing I might look for, though, then is substitution. And that's pretty much true of any time you're looking at a product or a quotient, is to maybe kind of look at substitution. But unfortunately, in this case, if you think about making u x squared plus 9x plus 14, then du would be 2x plus 9, and you don't have that in the numerator, and you don't have anything that you could just somehow adjust by a constant multiple to make it the numerator. So this substitution is not going to work. Again, I would do that. I would always check substitution, because substitution is less work than integration by partial fractions. And that doesn't mean it's necessarily easier or easier to spot, but it will go faster. So it's not going to, the old techniques aren't going to work. It's not a product, so we're not going to use integration by parts. Substitution doesn't work, so we are down to trying partial fractions. So the first thing I would do is look to factor the denominator. So I've got x plus 2 and x plus 7. So kind of my work to the side is I say, well, a over x plus 2 plus b over x plus 7 has to be equal to the original function. So thinking about finding a common denominator, and again, hopefully you've watched the video on why this technique works, but if you multiplied a by x plus 7 on both the top and the bottom, and you multiply b by x plus 2 on the top and bottom, then of course you should end up with a denominator that is common on both sides. Again, hopefully you've watched the video on this. This is just an example, one more example. This is not the first time you should be seeing this. But we multiply this by x plus 7 over x plus 7. We multiply this one by x plus 2 over x plus 2. So now the denominators are the same on either side of the equal sign, which means the numerators must be the same. And at this point, you pick the easiest possible x's. So let's pick x equals negative 7. So what happens, of course, is this is gone. Negative 7 plus 7 times a is 0. And negative 7 plus 2, this becomes negative 5b over here. Negative 7 times negative 7 is negative 49, plus 39 is negative 10. So what we find is that b is equal to 2. And I might even go back up right away and write that. Sometimes you find those numbers correctly and then you accidentally make a mistake of putting them in the wrong spot after you went to the work to find them correctly. The other x I'm going to pick is going to be x equals negative 2. And again, the purpose of that is just to get this thing to be gone. So negative 2 plus 7, I've got 5a. 7 times negative 2 is negative 14. Plus 39 is 25. So a is 5. And again, I might just write that up here right away. Now what this does for us, and I'm just going to kind of draw this arrow down, is it allows us to rewrite our integral as a sum of two fractions that are equivalent to the original fraction. One of those fractions is 5 over x plus 2. The other is 2 over x plus 7. And you are now allowed to split those integrals into separate ones because they're being added. Like that. And for me, at this point, I would always pull the constant multiplier out front. So bringing the 5 out, like that. Bringing the 2 out, that leaves us with just a 1, top and bottom. And then I integrate. Well, the integral of 1 over x plus 2 is the natural log of x plus 2. And it's still being multiplied by 5. The integral of 1 over x plus 7 is the natural log of x plus 7. There's still a 2 out front. Kind of running out of room for the plus c, but I'll see if I can't fit it in there. And here is my integral. Now sometimes you'll see, some work being done beyond this of, well, it's 2 that are being added together, so I could multiply the logs, but I'm going to stop right there because I wanted to show the example of the calculus, not necessarily the algebra that simplifies it, but you may need to check the back of your book to know if they keep going further with this.